Somewhere out there, two black holes are spiraling toward each other. They have been for millions of years, slowly at first, then faster still, until finally, in a fraction of a second, they collide, and in that single moment they release more energy than every star in the observable universe combined. Not light, not heat, something stranger, a ripple. Moving outward through the fabric of space itself at the speed of light, stretching and compressing reality as it travels, crossing galaxies, crossing voids, crossing 1 billion years of empty space, until it reaches a small blue planet, passes through every mountain and ocean and living thing on its surface, and disappears out the other side. We felt it. That's where this story begins. Not with an apple falling from a tree, not with a textbook equation, but with the fact that space itself can shake, and that we, on this tiny world, built something sensitive enough to feel it. Because what that ripple tells us about gravity is not what most people were ever taught. What is actually bending when light wraps around a dying star? Why does time, real, measurable, physical time, run slower on the surface of the Earth than it does in orbit? What is the invisible substance that makes up 85% of all the matter in the universe, that holds entire galaxies together, that we have never once directly seen? Why do the most massive objects in existence, black holes, eventually vanish, evaporating into faint radiation until nothing remains? What happened in the first fraction of a second after the Big Bang, before any star, any planet, any atom had ever existed? And what does any of this have to do with the weight you feel in your body right now? Tonight, we're going to go looking for answers, slowly, all the way from the surface of this planet to the edges of the observable universe and back again. If this kind of deep, unhurried journey through the cosmos is what you come here for, like or a subscribe genuinely helps this channel keep going, now let's go. For most of human history, the motion of things falling and the motion of celestial bodies were considered completely separate phenomena. Things fell because that was their nature. The heavens moved because angels or crystalline spheres carried them along. The earth and the sky operated under different rules. That changed in the 17th century, when Isaac Newton, working partly during a period of isolation during a plague epidemic, pieced together a mathematical framework that unified both. Published in 1687 in his landmark work, The Principia, Newton's law of universal gravitation proposed something audacious: that the force pulling an apple toward the ground and the force keeping the moon in its orbit around Earth were the exact same force. Every object with mass, Newton said, attracts every other object with mass. The strength of that attraction depends on two things: how much mass the objects have and how far apart they are. Specifically, the gravitational attraction between two objects is proportional to the product of their masses, and it falls off with the square of the distance between them. Double the distance, and the gravitational pull drops to 1/4 of what it was. Triple the distance, and it falls to 1/9. This was revolutionary. People had assumed the heavens were governed by something altogether different and higher than earthly physics. Newton said no. One set of equations covers everything, and the equations worked beautifully. They predicted how fast objects fall. They explained why the moon follows the path it does. They predicted the orbital periods of the planets to extraordinary precision. They explained ocean tides, the rise and fall of the sea driven by the moon's gravitational pull, which is slightly stronger on the side of Earth facing the moon than on the far side. Most spectacularly, Newton's gravity allowed scientists to discover planets they had never seen. In the mid-19th century, astronomers noticed that Uranus wasn't moving quite the way the equations predicted. Something was pulling it slightly off course. In 1846, two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where an unknown planet would have to be to cause those deviations. When astronomers pointed their telescopes to that spot in the sky, Neptune was exactly where the math said it would be. A planet discovered by gravity before it was ever directly observed. The power of Newton's framework was breathtaking. For over 2 centuries, Newton's laws were the final word. They were taught, they were used, they were trusted with the kind of confidence that comes from never once being wrong. But they weren't quite complete. The first hint that something deeper was waiting came from Mercury, the innermost planet baking in the glare of the Sun. Mercury's orbit is an ellipse, and like all planetary orbits, it slowly rotates over time. The point of closest approach to the Sun, called the perihelion, drifts forward with each passing orbit. Most of this drift could be explained by the gravitational tugs of the other planets, but there was a residual, roughly 43 arc-seconds of unexplained precession per century. That's less than 1/80th of a single degree per 100 years. Extraordinarily small, but real, and nobody could account for it. Some astronomers proposed a hidden planet called Vulcan, orbiting close to the Sun, too bright to easily observe. Systematic searches found nothing. Newton's equations were tweaked and adjusted. Nothing worked. For 50 years the mystery sat there, a hairline crack in an otherwise impeccable edifice. Then in 1915, Albert Einstein closed it with a single elegant theory, and in doing so turned our understanding of space, time, and gravity completely inside out. Einstein's general theory of relativity says that gravity is not a force at all. Let that sit for a moment. Everything you have ever been told about gravity being a force that pulls things toward massive objects, all of that, while useful as a practical approximation, is not the fundamental truth. The fundamental truth is something else entirely, and it begins with the fabric of the universe itself. To understand it, we first need to talk about space-time. In everyday life, we think of space and time as completely different things. Space is where things are. Time is when things happen. You can move around in space freely. Forward, backward, left, right, up, down. But time marches on regardless. You can't move backward through it. They feel like different kinds of things. Einstein showed this intuition is wrong. Space and time are not separate. They are two aspects of a single unified structure, space-time. Not space and time woven loosely together, but genuinely one, 4-dimensional fabric. Every event in the universe has both a location in space and a moment in time, and these are inseparable coordinates in the same geometric reality. Here is where it gets extraordinary. Space-time is not rigid. It is not a fixed stage that the universe performs on. It is dynamic. It bends. It curves. And what causes it to curve? Mass and energy. Any object that contains mass or energy, from a grain of sand to a supermassive black hole, distorts the space-time surrounding it. The more massive the object, the more severe the distortion. Earth curves space-time. Our sun curves it far more dramatically. You, sitting wherever you are right now, curve space-time a tiny but non-zero amount. Everything does. Now here's the part that changes everything. When an object moves through space-time, it naturally follows the most direct possible path, what mathematicians call a geodesic. In flat, undistorted space-time, a geodesic is a straight line. But in curved space-time, the most direct path is itself curved following the contours of that curvature. When you drop a ball and it falls toward the floor, the ball is not being dragged down by an invisible force. It is following the straightest available path through space-time that has been curved by the Earth beneath it. The path just happens to curve toward Earth's center, because that's where Earth's mass has distorted the geometry of space-time most strongly. There's a common mental image used to describe this. A heavy ball placed on a stretched rubber sheet, creating a depression that nearby smaller balls roll into. It's useful for building intuition, but it has real limitations. The rubber sheet is 2-dimensional, and it's using ordinary downward gravity to make the ball sink. That's circular when we're trying to explain gravity. Space-time is 4-dimensional, and its curvature is intrinsic. A property of the geometry itself, not a bending into some higher space outside it. The deeper truth is this. In the curved geometry of space-time, what looks like falling toward Earth is actually an object following the most natural straight-line equivalent path available to it. Gravity isn't pulling anything. The geometry of space and time itself is guiding the motion. This reframing has a profound consequence. It explains something that Newton's theory handled only as a mysterious coincidence. In Newtonian mechanics, the gravitational force on an object is proportional to its mass, but the acceleration produced by any force is inversely proportional to mass. These two factors cancel perfectly, meaning every object, regardless of how heavy or light, accelerates toward Earth at exactly the same rate. A feather and a bowling ball in the absence of air fall together. Newton had no explanation for why this should be true. It just was. In general relativity, it makes complete sense. Objects aren't being pulled by a force scale to their mass. They're all following the same geometric path through curved space-time. The curvature doesn't care about mass. All objects follow the same geodesics. Of course, they all fall at the same rate. It would be strange if they didn't. Apollo 15 astronaut David Scott demonstrated this on the lunar surface in 1971. Dropping a hammer and a feather simultaneously in the near vacuum of the moon's surface. They hit the ground at precisely the same moment. Not magic, geometry. Here is something that general relativity reveals which is genuinely disorienting once you let it in. Right now, if you're resting on a surface, you feel weight. You feel the pressure of whatever you're sitting or lying on. In ordinary language, we'd say gravity is pulling you down. But Einstein's framework inverts this entirely. The natural state of motion in curved space-time is freefall, an object that is not being pushed or pulled by any mechanical or electromagnetic force is in its most natural condition when it is freely following its geodesic. When you jump off a diving board and are airborne, before you hit the water, you're momentarily in a state of genuine freefall. You feel weightless. If you could somehow stay in that state indefinitely, if the ground never came, you would feel no weight at all. Astronauts aboard the International Space Station aren't experiencing weightlessness because they are far from Earth's gravity. The space station orbits at roughly 400 kilometers above the surface, where Earth's gravitational influence is still about 90% as strong as at ground level. They feel weightless because they are in constant freefall. The station and everyone inside it are all falling toward Earth together, while simultaneously moving sideways fast enough to keep missing the planet. A perpetual fall, curving just as the curvature of Earth curves away beneath them. The weight you feel right now isn't caused by gravity pulling you down. It's caused by the electromagnetic forces of the surface beneath you pushing you up, preventing you from following your natural geodesic through curved space-time. The floor is constantly shoving you away from the path your body would naturally take. What we call weight is the sensation of being accelerated away from freefall. Think about an elevator with its cable cut. As the elevator plunges downward, you'd float inside it. You'd feel weightless. Nothing would push you against the floor. Now, imagine you're in a rocket in deep space, far from any planet, and the rocket is accelerating at 9.8 meters per second squared, the same rate as Earth's surface gravity. You'd feel pressed to the floor in exactly the way you do on Earth right now. From the inside, you could not perform any experiment to distinguish between these two situations. This is Einstein's equivalence principle. The experience of standing in a gravitational field is locally indistinguishable from the experience of being in an accelerating reference frame. The two situations are physically equivalent, and from this principle flows one of the strangest verifiable facts in all of physics. Time itself runs at different rates depending on where you are in a gravitational field. Gravitational time dilation is one of those ideas that sounds like it must be science fiction, but is instead completely confirmed experimental physics. Time passes more slowly in stronger gravitational fields. The closer you are to a massive object, where space-time is more severely curved, the more slowly your clocks tick relative to clocks farther away. This is not a perceptual effect. It is not that time feels slower. Time actually physically passes at a different rate. The effect has been measured countless times. In 1971, physicists Joseph Heffel and Richard Keating placed highly accurate atomic clocks on commercial aircraft and flew them around the world in both directions. When the clocks returned and were compared to identical clocks that had stayed on the ground, they showed differences of exactly the magnitudes predicted by general relativity, accounting for both the altitude and the motion of the aircraft. The differences were measured in nanoseconds, but they were real. Every time you use GPS navigation on your phone, you're relying on gravitational time dilation being real and precisely accounted for. The atomic clocks aboard GPS satellites orbit Earth at altitudes of roughly 20,000 kilometers, where gravity is weaker than on the surface. Those clocks run slightly faster than clocks on the ground. If the system didn't correct for this, applying Einstein's equations automatically, position errors would accumulate at a rate of several kilometers per day. Your phone's navigation app would be useless within hours. The entire global positioning system is a practical application of general relativity operating in the background, invisibly every single day. Scientists at the National Institute of Standards and Technology demonstrated in 2010 that they could detect gravitational time dilation over a height difference of just 33 centimeters, roughly the height of a large coffee mug placed on a table. The higher clock ticked faster. The difference was approximately 90 trillionths of a second per day. But it was real, and it was exactly what Einstein's equations predicted. The closer you approach a massively dense object, the more extreme this effect becomes. Near a neutron star's surface, time passes roughly 30% more slowly than in open space far from any mass. Near the event horizon of a black hole, the time dilation becomes so extreme that, from the perspective of a distant observer, an infalling object appears to slow to a stop and freeze, its light red-shifting to nothing. From the perspective of the object itself, nothing unusual happens at the horizon. It passes through. But these two perspectives, the outside observer and the falling traveller, are both correct descriptions of the same physical reality, just as seen from different positions in curved space-time. Perhaps nothing in physics captures the imagination, and genuinely deserves to, quite like a black hole. A black hole is a region of space-time curved so severely that the geometry itself closes. Every path through space-time within a certain boundary, the event horizon, leads inward toward the centre. Not because something pulls everything in, but because the geometry of space-time has been distorted to the point where all possible directions in that region point toward the singularity at the core. There is no path that leads out. It is not that escape would require moving faster than light. It is that outward is not a direction that exists anymore inside the event horizon. All future-pointing paths in space-time lead inward. Black holes form primarily from the deaths of massive stars. A star exists in a constant gravitational negotiation. The crushing inward pull of its own mass balanced against the outward pressure generated by nuclear fusion in its core. As long as fusion continues, the star holds itself up. For a star like our Sun, this equilibrium lasts roughly 10 billion years. For stars much more massive, greater than about 20 times the mass of the Sun, the final stages of stellar evolution end catastrophically. When the core of such a star runs out of fusible fuel, the fusion stops. The outward pressure vanishes. There is nothing to resist gravity. The core collapses in less than a second. If the remaining mass exceeds a critical threshold, the collapse proceeds without limit, compressing all that mass into what our equations describe as a singularity, a point of theoretically infinite density, where the curvature of space-time diverges to infinity and our equations break down entirely. Surrounding that singularity is the event horizon. The distance from the singularity to the event horizon is called the Schwarzschild radius, named for Karl Schwarzschild, who derived it just weeks after Einstein published general relativity in 1915, while stationed on the front lines of World War I. For a black hole containing the equivalent of our Sun's mass, this radius would be about 3 kilometers. For the stellar mass black holes that typically form from supernova collapses, ranging from a few to several tens of solar masses, the event horizon is tens of kilometers across. For supermassive black holes, the titanic structures lurking at the hearts of galaxies, the event horizons can be billions of kilometers in radius, larger than our entire inner solar system. One of the most common misconceptions about black holes is that they vacuum up everything around them. They don't. A black hole exerts exactly the same gravitational influence as any other object of the same mass. If the Sun was somehow replaced by a black hole of identical mass, which won't happen, the Sun isn't massive enough, and even if it were, we'd face other problems. Earth's orbit would not change at all. We'd continue circling at the same distance in the same period. We'd freeze in the dark, but we wouldn't spiral in. The danger is proximity. Because a black hole's physical surface is inside the event horizon, rather than at a visible stellar radius, you can get far closer to the concentrated mass than you ever could to a normal star. And as you get closer, something terrible begins to happen. Tidal forces. Tidal forces arise whenever gravity pulls unequally across an extended object. The same phenomenon drives Earth's ocean tides, because the Moon's gravity is slightly stronger on the near side of Earth than on the far side. Near a sufficiently small black hole, these tidal forces become devastating long before the event horizon. If you fell feet first towards such an object, the pull on your feet would exceed the pull on your head by a catastrophic margin. The difference would stretch you along the radial direction while compressing you transversely. Astrophysicists refer to this process, with characteristic dry humour, as spaghettification. The word appears in peer-reviewed scientific literature. You would be stretched into a thin stream of particles and gas, spiralling inward. For supermassive black holes, however, the mathematics works out differently. The event horizon is so far from the singularity, billions of kilometers for the largest examples, that tidal forces at the horizon itself are actually quite mild. In principle, you could cross the event horizon of a sufficiently massive black hole without immediately experiencing anything dramatic. You would have no way of knowing you had crossed it. No signs, no signals, just the smooth continuation of your fall. It's only much later, as you drew closer to the singularity, that tidal forces would become lethal, and by that point, it would no longer matter because you couldn't escape regardless. Black holes are also, somewhat paradoxically, not entirely black. In 1974, the physicist Stephen Hawking combined quantum mechanics with the mathematics of general relativity and discovered that black holes should emit a faint glow of thermal radiation, now called Hawking radiation. The mechanism involves quantum uncertainty near the event horizon, where the mathematics of quantum field theory permits the spontaneous appearance of particle-antiparticle pairs out of the energy budget of the gravitational field. Occasionally one particle escapes while the other falls inward, carrying away energy from the black hole. Over immense timescales, this process causes black holes to slowly lose mass and ultimately evaporate. For large black holes, this evaporation proceeds on timescales that are difficult to even express meaningfully. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to fully evaporate, a number so much larger than the current age of the universe that ordinary comprehension fails. The universe is approximately 13.8 billion years old, which is about 10 to the power of 10 years. The evaporation time for a solar mass black hole is 10 with 67 zeros, incomparably longer than anything else in physics. For tiny hypothetical primordial black holes, formed in the extreme conditions of the early universe, evaporation could be fast enough to have already completed. Their final moments would release enormous bursts of energy. We have not detected evidence of such evaporation events, which constrains theories about whether primordial microblack holes exist. If space-time is a physical fabric, something that can stretch and curve, then it should be possible to send waves through it, just as you can send ripples through water by by disturbing its surface. Einstein predicted this in 1916, just months after completing general relativity. Accelerating masses, he showed, should produce ripples propagating outward through space-time at the speed of light. These gravitational waves would alternately stretch and compress space in perpendicular directions as they passed, cycling with the frequency of the source. He also immediately estimated that these waves would be almost unimaginably weak. Even the most violent events in the universe, two massive stars colliding, would produce distortions so tiny by the time they reached Earth that Einstein doubted they could ever be detected. He wrote them off as a theoretical curiosity, probably forever beyond the reach of measurement. He was wrong about the detection part. In 2015, a century after, Einstein made his prediction. Engineers and physicists at the Laser Interferometer Gravitational Wave Observatory, LIGO, caught a gravitational wave for the first time. The signal had travelled 1.3 billion light-years. By the time it arrived on Earth, the distortion it carried amounted to a change in length of roughly 1/10,000th, the diameter of a proton across a 4-kilometre long laser beam, less than a billionth of a metre. The comparison scientists often use, it's like trying to measure the distance to the nearest star with a precision better than the width of a human hair. The source of this first detected wave was a pair of black holes, one roughly 29 times the mass of the Sun, the other about 36 solar masses, that had been spiralling inward toward each other over billions of years, losing energy to gravitational radiation, until they finally merged into a single black hole. The merger happened in a fraction of a second. In those final moments, the energy radiated away in gravitational waves exceeded the combined light output of every star in the observable universe combined. That's not rhetorical inflation. That is the actual calculated power output of that event during that fraction of a second. Here is something worth pausing on. 29 plus 36 is 65, but the resulting black hole had a mass of 62 solar masses. 3 solar masses vanished. That mass was converted entirely into gravitational wave energy via Einstein's famous E equals mc squared. 3 times the mass of our entire Sun, annihilated in an instant and radiated outward through the cosmos as ripples in space-time. Since that first detection, LIGO and its partner observatories, including the Virgo detector in Italy, have accumulated dozens of gravitational wave events. Most have been black hole mergers, but some have been collisions between neutron stars, which turn out to be scientifically even richer. In 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars spiraling into each other. Unlike black hole mergers, this event also produced light, an enormous burst of gamma rays, followed by optical and infrared afterglow, visible to traditional telescopes around the world. It was the first time a single astronomical event was observed in both gravitational waves and electromagnetic radiation simultaneously. Astronomers called it the dawn of multi-messenger astronomy. The implications went beyond a single discovery. By comparing the arrival times of the gravitational waves and the gamma rays, which arrived with a delay of about 1.7 seconds, consistent with the time it takes for the gamma burst to form, scientists could confirm that gravitational waves travel at the speed of light to extraordinary precision. This wasn't guaranteed by theory alone. Some proposed alternatives to general relativity predicted different speeds. Those theories are now ruled out. The neutron-star merger also produced heavy elements. Like curves in the days after the event, matched theoretical predictions for what happens when neutron-rich material is ejected and undergoes rapid neutron capture. The astrophysical process, called the R process, responsible for producing heavy elements like gold, platinum, and uranium. The gold in a wedding ring, the platinum in a catalytic converter, produced in events like this one, scattered across the cosmos, eventually incorporated into planetary systems like ours. Gravitational waves are not merely a spectacular confirmation of general relativity. They represent an entirely new form of astronomy, light can be blocked, scattered, and absorbed by intervening gas and dust. Gravitational waves pass through matter almost entirely without interaction. They carry information from events that produce no light at all, or that are hidden behind veils of material opaque to electromagnetic observation. They let us see the universe in a completely new register. One of the first and most dramatic confirmations of general relativity came just 4 years after Einstein published the theory. In May 1919, a total solar eclipse crossed South America and the coast of West Africa. British astronomer Arthur Eddington organised 2 expeditions to observe it, one to the island of Príncipe off the coast of Gabon and one to Sobral in Brazil. The goal was to photograph stars whose light grazed the solar disk during the eclipse, when the sun's glare was blocked by the moon. In flat space-time, starlight travels in straight lines and appears to come from its actual position in the sky. But if general relativity was right, if mass curves space-time and light follows that curvature, then starlight passing near the sun should have its path bent. Stars near the sun's edge in the sky should appear very slightly displaced from their known catalogue positions. Newton's theory of gravity also predicted some bending, treating photons as particles subject to gravitational attraction. But Einstein's prediction was twice as large as Newton's, because general relativity accounts for the curvature of time as well as the curvature of space. Eddington's measurements showed displacement of approximately 1.75 arcseconds, close to 1/2000th of a degree, for stars near the solar limb. This matched Einstein's prediction, not Newton's. The news of the results spread across the world almost instantly. The New York Times reported it prominently. Einstein became one of the most famous scientists in history virtually overnight. We now use the phenomenon Eddington measured, gravitational lensing, as a precision tool throughout astronomy. When light from a distant galaxy passes near a massive foreground object, such as another galaxy or a galaxy cluster, the space-time curvature bends the light along multiple paths. The result can be multiple images of the same distant source arranged symmetrically around the lensing object, arcs of light stretched across the sky, or in ideal alignment, complete rings, called Einstein rings, where the background source is smeared into a perfect circle surrounding the lensing mass. By analysing the geometry and brightness of these lensed images, astronomers can reconstruct the distribution of mass in the lensing object. Crucially, this technique responds to all mass, regardless of whether that mass emits light. It is currently one of the most powerful tools we have for mapping dark matter, the invisible substance that makes up approximately 85% of all matter in the universe, but produces no light, no radio waves, no X-rays. Dark matter curves space-time, and curved space-time bends light, and bent light carries a signature. Even the invisible leaves a mark. Gravitational lensing has also found exoplanets. When a foreground star passes almost exactly between Earth and a more distant background star, the foreground star's gravity focuses the background starlight into a brief brightening event, a gravitational microlensing transient. If the foreground star has a planet, that planet introduces a second, shorter brightening spike within the event. This technique has revealed dozens of worlds orbiting stars across the galaxy, including planets that would be impossible to detect by other methods. General relativity doesn't just describe the behavior of individual objects, it describes the structure and evolution of the universe itself. In 1922, the Russian mathematician Alexander Friedmann solved Einstein's field equations for the universe as a whole and found something disturbing. The equations didn't allow for a static universe. The solution required space itself to be either expanding or contracting. Einstein initially resisted this. He even introduced an ad hoc term into his equations, which he called the cosmological constant, specifically to force a static solution. Then, in 1929, Edwin Hubble published observations showing that distant galaxies are all moving away from us, with a recession velocity proportional to their distance. The farther away a galaxy was, the faster it was receding. Space itself was stretching. Einstein later called the cosmological constant his greatest blunder. If the universe is expanding now, it was smaller in the past. Wind the clock. Backward far enough and all the matter and energy in the observable universe converges toward a single point of extraordinary temperature and density, the Big Bang. Not an explosion within space, but the expansion of space itself, beginning from an initial state that our current physics cannot fully describe. The evidence for this origin is overwhelming. Galaxies are moving apart, consistent with expansion. The universe is bathed in microwave radiation coming uniformly from every direction. The cosmic microwave background, the thermal afterglow of a time roughly 380,000 years after the Big Bang, when the universe first became cool enough for neutral hydrogen to form and light to travel freely. The relative abundances of hydrogen, helium, and trace amounts of lithium in the cosmos match precisely the predictions of Big Bang nucleosynthesis, the nuclear reactions that occurred in the first few minutes after the universe began. 3 independent lines of evidence, all converging on the same story. The Big Bang implies that time itself began with the universe. It makes no sense to ask what existed before the Big Bang, because before is a temporal concept, and time is part of space-time, which came into existence with the universe. The question dissolves under scrutiny. It's like asking what lies north of the North Pole. In 1998, 2 independent research teams studying distant type Ia supernovae made a discovery so unexpected that many physicists initially refused to believe it. The expansion of the universe is accelerating. After the Big Bang, everyone expected gravity to be gradually slowing the expansion, the way throwing a ball upward causes it to slow as it rises. The question was only whether the universe had enough mass to eventually reverse and collapse, or too little to stop expanding. What nobody expected was for the expansion to be speeding up. Something is pushing space apart. We call it dark energy. We don't know what it is. The leading interpretation is that it represents an intrinsic energy of empty space itself, a cosmological constant, the very term Einstein introduced and then abandoned. But unlike Einstein's original use, there is now observational evidence demanding it. Approximately 68% of the universe's total energy content appears to be dark energy. Another 27% is dark matter, gravitationally active but electromagnetically invisible. Ordinary matter, the stuff we can see, the stuff we and our instruments are made of, accounts for only about 5%. We live in a universe where 95% of everything is made of substances we cannot directly detect and do not fully understand. That is not a rhetorical provocation. That is the current state of cosmological knowledge. What we do know about dark matter comes almost entirely from its gravitational effects. We know it exists in large quantities in and around galaxies because the rotation curves of spiral galaxies, the speeds at which stars orbit the galactic center at different distances, require far more mass than we can account for with visible stars and gas. Outer stars rotate as fast as inner ones, which they would not do if only visible matter were present. The gravitational influence of an extended halo of invisible mass explains the observations. We know dark matter clusters gravitationally. It forms halos. It participates in the formation of large-scale structure. It acts as the skeleton upon which ordinary matter assembles into galaxies and filaments. Simulations that include dark matter reproducing something matching the observed cosmic web are among the most striking confirmations that it is real. Without it, the universe would look completely different at large scales. Galaxies would not have formed as they did. The cosmic web we observe would not exist. What dark matter is made of, what particles it consists of, whether it is a single type or several, whether it has any interactions other than gravitational remains entirely unknown. Experiments in deep underground laboratories, surrounded by enough rock to filter out nearly all other particles, have searched for dark matter particles colliding with ordinary atomic nuclei. So far, no definitive detection. Particle accelerators have searched for dark matter particles produced in high-energy collisions. Nothing conclusive. The search continues on multiple fronts, with new ideas about what dark matter might be emerging regularly. It remains one of the most important open questions in physics. Dark energy is even more enigmatic. Its existence is inferred from a single observational signature, the acceleration of cosmic expansion, and we have essentially no theoretical handle on what it is or why it has the value it does. The value predicted by naive quantum field theory for the vacuum energy that dark energy might represent is approximately 120 orders of magnitude larger than the observed value. This is sometimes called the worst prediction in the history of physics. Understanding why dark energy has the small value it does, and why it has that value now rather than at some other epoch of cosmic history, is one of the deepest puzzles facing theoretical physics. The acceleration of expansion has profound implications for the future. The galaxies beyond our local cluster, the gravitationally bound group of roughly 80 galaxies including the Milky Way, Andromeda and their satellites, are already receding from us. In billions of years they will recede faster and faster, eventually crossing the boundary beyond which their light can never reach us. The observable universe will shrink. Cosmology will become impossible for any civilization arising in the far future. They will look out and see only their own galaxy, and perhaps a handful of neighbours, with no evidence that anything lies beyond. The universe's history, written in the light of distant galaxies, will have been swallowed by expansion. We are fortunate to exist at a moment when it can still be read. Let's take a moment to pull back and watch gravity at work across the full range of scales the universe offers. At the planetary level, gravity sculpts everything from the inside out. When Earth was young and still molten, gravity sorted its constituent materials by density. The heaviest elements, iron and nickel, sank toward the centre to form the core. Lighter silicates rose toward the surface to form the mantle and crust. The convection of liquid iron in the outer core, driven by heat from radioactive decay and sustained by gravitational pressure, generates Earth's magnetic field, the shield that protects the surface from the most energetic charged particles streaming from the Sun. Without gravity sorting those materials, no magnetic field. Without the magnetic field, the surface might resemble Mars. At the solar system scale, gravitational resonances produce intricate structure. The gaps in Saturn's rings, the most prominent being the Cassini division, occur where orbital periods would be simple fractions of the periods of Saturn's larger moons. Particles in those regions receive repeated gravitational nudges in the same phase of their orbit, which accumulates over time into enough perturbation to push them elsewhere. The resulting gaps are maintained against refilling by the same orbital mechanics that cleared them. The asteroid belt likewise bears the imprint of Jupiter's gravity, with Kirkwood gaps at orbital radii corresponding to resonances with the giant planet's orbital period. At the stellar level, gravity both creates and destroys. Dense knots within enormous molecular clouds, regions of cold hydrogen and dust many light years across, begin to collapse under their own gravity when some disturbance tips the balance. As material falls inward, gravitational potential energy converts to heat. The collapsing cloud fragments and heats. Eventually, if the concentration is sufficient, the centre reaches temperatures of millions of degrees and nuclear fusion ignites. A star is born. Gravity assembled it. For billions of years, the star burns in hydrostatic equilibrium, the inward pressure of gravity precisely balanced by the outward pressure from fusion energy. In the Sun's case, this has been going on for 4.6 billion years and will continue for roughly another 5 billion. Then, when the hydrogen in the core runs out and the core begins to contract, the outer layers will swell into a red giant engulfing the inner planets, before the outer layers are gently expelled, and the core settles into a white dwarf, a dense, cooling ember about the size of Earth. For stars more than about 8 times the mass of the Sun, the ending is more violent. Successive fusion stages build heavier and heavier elements in nested shells, hydrogen to helium, helium to carbon, carbon to oxygen, neon, silicon. Each stage is shorter than the last and releases less energy. When the core accumulates iron, fusion stalls. Iron is the most tightly bound nucleus. Fusing it consumes energy rather than releasing it. In a fraction of a second, gravity wins completely. The iron core collapses to nuclear density. The collapse bounces, sending a shock wave tearing through the outer layers. The star explodes as a supernova, briefly outshining the entire galaxy containing it. The explosion scatters carbon, oxygen, calcium, iron, and heavier elements forged by the dying star across the interstellar medium. These atoms drift for millions of years in the tenuous gas between stars, occasionally encountering regions where gravity causes new collapse, new star formation. Our Sun and solar system formed from material already enriched by several previous generations of stars that lived and died before us. The calcium in your bones, the iron that carries oxygen in your blood, the oxygen you breathe, all were synthesized in stellar interiors and scattered by explosions, gathered by gravity, incorporated into a planet, and eventually assembled into you. Gravity is why you exist. Gravity made the stars that forged your atoms. Gravity gathered those atoms into a solar system. Gravity shaped Earth into a stable planet with liquid water. In a very deep sense, you're a temporary organization of matter that gravity has been assembling for billions of years. At galactic scales, gravity binds collections of hundreds of billions of stars into the rotating disks and ellipsoids we call galaxies. The Milky Way stretches roughly 100,000 light-years across and contains somewhere between 200 and 400 billion stars. Our Sun sits about 26,000 light-years from the galactic centre, orbiting at a speed of roughly 220 kilometers per second. One full orbit, a galactic year, takes approximately 225 million years. The last time the Sun was at its current position in its orbit, the Triassic period was just beginning on Earth. Our own galaxy is currently absorbing the Sagittarius Dwarf Elliptical Galaxy, a small, companion galaxy that has made several close passes and is being tidally shredded, its stars drawn out into long streams wrapped multiple times around the Milky Way. In roughly 4 billion years, we will begin merging with the Andromeda Galaxy, currently approaching at about 110 kilometers per second. The merger will unfold over hundreds of millions of years, producing spectacular distortions, bursts of star formation as gas clouds collide and compress, and eventually a merged elliptical galaxy with a central supermassive black hole assembled from the cores of both galaxies. Individual stars will rarely collide, the distances are too vast, but gravitationally, the two galaxies will become one. At the largest scales, galaxies are not randomly scattered through the universe. Gravity has organized them into a cosmic web, vast filaments of matter stretching hundreds of millions of light-years, intersecting at dense nodes where galaxy clusters form, surrounding enormous voids, nearly devoid of visible matter. This structure grew from tiny density fluctuations imprinted on the universe in its earliest moments. Regions slightly denser than their surroundings, which gravity then amplified over billions of years. The large-scale structure of the universe is a record of gravity at work over the entire history of cosmic time. General relativity has passed every test it has ever been given. It is one of the most precisely tested theories in all of science, and yet we know with certainty that it is incomplete. The source of this certainty is not experimental failure. No observation has ever contradicted general relativity. The source is theoretical. General relativity and quantum mechanics are fundamentally incompatible descriptions of reality. Quantum mechanics governs the behavior of matter at the smallest scales. It is probabilistic at its core. Before a quantum system is measured, it does not have definite properties. It exists in a superposition of possible states, described by a wave function that encodes the probability of each outcome. Measurement collapses this superposition, selecting one outcome from the distribution. There is genuine irreducible randomness built into the foundations of quantum theory. General relativity could not be more different. It is completely deterministic, knowing the geometry of space-time and the distribution of mass and energy at one moment allows you to calculate both the past and future with perfect precision. No probabilities, no superpositions, no uncertainty beyond what measurement adds. For the vast majority of physical situations, these theories never need to coexist. Quantum mechanics handles atoms and particles. General relativity handles stars and galaxies. The scales are so different that neither theory needs to worry about the other. But there are situations where both matter simultaneously. Inside a black hole, as matter collapses toward the singularity, it is compressed to a scale where quantum effects are unavoidable. But the space-time curvature is simultaneously becoming infinite. Our equations break down there. We cannot describe what actually happens at a black hole's core with any existing theory. The same problem appears at the very beginning of the universe. In the first instance after the Big Bang, the entire observable universe was compressed into a region smaller than an atom. Quantum mechanics and general relativity were both essential, and they contradicted each other. We cannot fully describe the first fraction of a second of cosmic history with any theory we currently possess. The search for quantum gravity, a theoretical framework that unifies quantum mechanics and general relativity, is arguably the central unsolved problem of fundamental physics. String theory proposes that the fundamental constituents of nature are not point particles, but tiny one-dimensional objects, strings, whose different vibrational modes correspond to different particles. The graviton, the hypothetical quantum particle mediating gravitational interactions, emerges naturally from string theory as one vibrational mode. String theory's mathematical self-consistency requires additional spatial dimensions beyond the three we experience, typically 6 or 7 extra dimensions compactified to sizes far below anything we can probe. The framework is mathematically intricate and generates genuine theoretical results, but has so far resisted producing testable predictions that distinguish it from other theories. Loop quantum gravity takes a different route, treating space-time itself as quantized, built from discrete units, a kind of granularity to the fabric of the universe at the Planck scale, approximately 10 to the minus 35 meters. Space would not be a smooth continuum but a weave of discrete geometric elements. The infinities that plague general relativity at singularities would be regulated by this discreteness. Loop quantum gravity also struggles with making clean, accessible experimental predictions, though the theoretical framework is internally consistent. There are hints we might look for. If space-time is granular at the Planck scale, photons of different energies travelling across cosmological distances might arrive at slightly different times, the granularity of the fabric introducing tiny energy-dependent delays. No such dispersion has been detected in gamma-ray observations of distant sources, which already constrains the scale at which any discreteness could operate. The universe appears smooth to a level far below what some early quantum gravity models predicted. One of the deepest puzzles in this space is the black hole information paradox. Quantum mechanics has a fundamental principle called unitarity. The evolution of any quantum state is reversible. Given a quantum state at one time, you can, in principle, run the equations backward and recover the exact state at any earlier time. Information is never truly lost, but Hawking radiation appears to violate this. When Hawking showed that black holes slowly evaporate, the radiation that emerges carries no information about what fell in. A black hole formed from collapsing hydrogen gas and a black hole formed from an equal mass of old paperback novels would emit identical Hawking radiation. The information about the infalling material would simply be gone. Hawking originally argued this was real, that black holes are the one place in the universe where information genuinely disappears, and that quantum mechanics breaks down in their vicinity. This was deeply controversial. Most theoretical physicists believed unitarity must be preserved, and that general relativity must somehow be modified at the horizon scale. Recent theoretical work, drawing on ideas from holography and quantum information theory, suggests that information is preserved in subtle correlations in the Hawking radiation, encoded in ways that are scrambled but not destroyed, like the information in a burned book, in principle recoverable though practically inaccessible. How exactly this mechanism works within a complete quantum gravity theory remains unresolved. The paradox has led to genuinely new ideas about the nature of spacetime itself. Some researchers now believe spacetime may be emergent, not a fundamental ingredient of reality, but something that arises from a deeper quantum description in which space and time are not primary concepts. The fabric of the universe might not be the foundation. It might be a consequence. Let's take a moment to pull back and watch gravity at work across the full range of scales the universe offers. At the planetary level, gravity sculpts everything from the inside out. When Earth was young and still molten, gravity sorted its constituent materials by density. The heaviest elements, iron and nickel, sank toward the centre to form the core. Lighter silicates rose toward the surface to form the mantle and crust. The convection of liquid iron in the outer core, driven by heat from radioactive decay and sustained by gravitational pressure, generates Earth's magnetic field, the shield that protects the surface from the most energetic charged particles streaming from the sun. Without gravity sorting those materials, no magnetic field. Without the magnetic field, the surface might resemble Mars. At the solar system scale, gravitational resonances produce intricate structure. The gaps in Saturn's rings, the most prominent being the Cassini division, occur where orbital periods would be simple fractions of the periods of Saturn's larger moons. Particles in those regions receive repeated gravitational nudges in the same phase of their orbit, which accumulates over time into enough perturbation to push them elsewhere. The resulting gaps are maintained against refilling by the same orbital mechanics that cleared them. The asteroid belt likewise bears the imprint of Jupiter's gravity, with Kirkwood gaps at orbital radii corresponding to resonances with the giant planet's orbital period. At the stellar level, gravity both creates and destroys. Dense knots within enormous molecular clouds, regions of cold hydrogen and dust many light years across, begin to collapse under their own gravity when some disturbance tips the balance. As material falls inward, gravitational potential energy converts to heat. The collapsing cloud fragments and heats. Eventually, if the concentration is sufficient, the center reaches temperatures of millions of degrees and nuclear fusion ignites. A star is born. Gravity assembled it. For billions of years, the star burns in hydrostatic equilibrium, the inward pressure of gravity precisely balanced by the outward pressure from fusion energy. In the Sun's case, this has been going on for 4.6 billion years and will continue for roughly another 5 billion. Then, when the hydrogen in the core runs out and the core begins to contract, the outer layers will swell into a red giant engulfing the inner planets, before the outer layers are gently expelled and the core settles into a white dwarf, a dense, cooling ember about the size of Earth. For stars more than about 8 times the mass of the Sun, the ending is more violent. Successive fusion stages build heavier and heavier elements in nested shells. Hydrogen to helium, helium to carbon, carbon to oxygen, neon, silicon. Each stage is shorter than the last and releases less energy. When the core accumulates iron, fusion stalls. Iron is the most tightly bound nucleus. Fusing it consumes energy rather than releasing it. In a fraction of a second, gravity wins completely. The iron core collapses to nuclear density. The collapse bounces, sending a shock wave tearing through the outer layers. The star explodes as a supernova, briefly outshining the entire galaxy containing it. The explosion scatters carbon, oxygen, calcium, iron, and heavier elements forged by the dying star across the interstellar medium. These atoms drift for millions of years in the tenuous gas between stars, occasionally encountering regions where gravity causes new collapse, new star formation. Our sun and solar system formed from material already enriched by several previous generations of stars that lived and died before us. The calcium in your bones, the iron that carries oxygen in your blood, the oxygen you breathe, all were synthesized in stellar interiors and scattered by explosions, gathered by gravity, incorporated into a planet, and eventually assembled into you. Gravity is why you exist. Gravity made the stars that forged your atoms. Gravity gathered those atoms into a solar system. Gravity shaped Earth into a stable planet with liquid water. In a very deep sense, you're a temporary organization of matter that gravity has been assembling for billions of years. At galactic scales, gravity binds collections of hundreds of billions of stars into the rotating disks and ellipsoids we call galaxies. The Milky Way stretches roughly 100,000 light-years across and contains somewhere between 200 and 400 billion stars. Our Sun sits about 26,000 light-years from the galactic centre, orbiting at a speed of roughly 220 kilometers per second. One full orbit, a galactic year, takes approximately 225 million years. The last time the Sun was at its current position in its orbit, the Triassic period was just beginning on Earth. Our own galaxy is currently absorbing the Sagittarius Dwarf Elliptical Galaxy, a small, companion galaxy that has made several close passes and is being tidally shredded, its stars drawn out into long streams wrapped multiple times around the Milky Way. In roughly 4 billion years, we will begin merging with the Andromeda Galaxy, currently approaching at about 110 kilometers per second. The merger will unfold over hundreds of millions of years, producing spectacular distortions, bursts of star formation as gas clouds collide and compress, and eventually a merged elliptical galaxy with a central supermassive black hole assembled from the cores of both galaxies. Individual stars will rarely collide, the distances are too vast, but gravitationally, the two galaxies will become one. At the largest scales, galaxies are not randomly scattered through the universe. Gravity has organized them into a cosmic web, vast filaments of matter stretching hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, surrounding enormous voids, nearly devoid of visible matter. This structure grew from tiny density fluctuations imprinted on the universe in its earliest moments. Regions slightly denser than their surroundings, which gravity then amplified over billions of years. The large-scale structure of the universe is a record of gravity at work over the entire history of cosmic time. We've travelled a long way tonight. From the feeling of weight in your body to the geometry of curved space-time. From Newton's revolutionary synthesis to Einstein's deeper truth. From falling apples to gravitational waves crossing 1 billion light-years of cosmic distance. From time running slower near massive objects to the possibility that space-time itself is not fundamental. Let me close with something worth sitting with. You're being pushed upward right now. Whatever surface supports you, floor, chair, bed, is exerting electromagnetic force against your body, preventing you from following your natural path through curved space-time. The thing we call weight, the heaviness you feel in your limbs when you're tired, the press of the mattress against your back, that is resistance to your natural geodesic. That is the universe refusing to let you fall freely. The weightlessness astronauts experience isn't an absence of anything real. It is the presence of something fundamental, the freedom to move as space-time curves. It is closer to the universe's natural mode than anything we experience with our feet on the ground. Meanwhile, across a universe 93 billion light-years in observable extent, the same geometric principles are in operation. Stars tracing their geodesics around galactic cores, galaxies following the curvature generated by vast webs of dark matter. Gravitational waves, ripples from cataclysms 1 billion years past, washing through you right now, stretching and squeezing space by an amount so minuscule it makes a proton look enormous. The universe is not a collection of objects in a static backdrop. It is a dynamic, self-curving, self-organizing geometry, and everything you see, including yourself, is a pattern within it. Einstein said the most incomprehensible thing about the universe is that it is comprehensible. We are creatures who evolved to find berries and avoid predators on a small rock orbiting an unremarkable star, in the outer spiral arm of one galaxy among hundreds of billions. And yet we have measured the curvature of space-time. We have detected the tremors of black holes merging before multicellular life existed on Earth. We have traced the history of the cosmos back to fractions of a second after the beginning. We have built devices sensitive enough to detect a change in length of less than 1,000th, the diameter of a proton. That is an extraordinary thing to be able to say about a species. Gravity shapes the conditions of our existence in ways both enabling and constraining. Stars would not exist without gravity to collapse hydrogen into dense enough conditions for fusion. Planets would not exist without gravity to aggregate the debris of stellar nurseries. The chemistry of life depends on liquid water, which requires a planet at the right temperature, orbiting the right kind of star, held in its orbit by gravity. Everything about our existence traces back in some way to the behavior of this one geometric property of space-time. Gravity limits us too. The stars are incomprehensibly far away, and the speed of light is a hard ceiling on how fast we can reach them. The distances between stellar systems mean that, in all likelihood, any interstellar journey would be measured in centuries or millennia from the perspective of those left behind. The same time dilation that slows clocks near massive objects also slows them for objects moving at near-light speeds, a relativistic effect that means a fast-moving traveller would age slowly while the universe around them rushed forward. Travel fast enough to reach a distant star in a human lifetime, and you return to a world centuries older than when you left. Every departure becomes permanent. The stars are not unreachable, but they extract a cost that no technology can fully mitigate. Still, we look up. We measure. We build instruments that can feel the tremble of space-time from unimaginably far away. We will build better ones. The question of quantum gravity, what the universe looks like at the deepest possible level, where space and time dissolve into something stranger and more fundamental, is still open. The nature of dark matter and dark energy remains an active mystery. The precise history of the universe's first instance is still beyond our reach. But every generation of humans has handed the next one a deeper and more accurate understanding. Newton gave us the tools to predict the planets. Einstein gave us the truth beneath the prediction. The next transformation is waiting somewhere. In a theorist's equations, in the data from a future gravitational wave detector, in an unexpected observation from a telescope not yet built. The universe is vast, and it is old, and it is patient, but it is not opaque. It has been, and continues to be, understood. Consider the arc of this understanding. Galileo in the early 17th century rolling balls down inclined planes, timing, then with his pulse, discovering that the distance travelled grows with the square of time. Kepler, working from the exhaustive observational records of Tycho Brahe, finding that planets trace ellipses and that the time to complete an orbit scales with the size of the orbit in a precise mathematical way without understanding why. Newton then providing the why, the gravitational inverse square law that made Kepler's empirical rules into logical necessities. And then Einstein, 3 centuries later, explaining the deeper mechanism beneath Newton's law, revealing that gravity isn't a force but a curvature, and that even Newton's description was an approximation of something more fundamental. Each layer of understanding preserved the predictive power of the layer before it, while revealing the deeper truth underneath. Newton's equations are still used today for spacecraft navigation, planetary calculations and engineering problems. They are excellent approximations when velocities are much less than the speed of light and gravitational fields are weak. General relativity reproduces Newtonian gravity in those limits, and only diverges when Newton's theory diverges from measurement, near black holes, in the early universe, in precise timing systems like GPS. The next layer, quantum gravity, will similarly reproduce general relativity in the appropriate limits. It will not overturn Einstein. It will deepen him in the same way Einstein deepened Newton. That is what science does. It does not discard the past. It understands it more completely. And somewhere in the next generation of experiments, in data from more sensitive gravitational wave detectors, in observations of the cosmic microwave background's polarization patterns, in laboratory tests of quantum systems near massive objects, in theoretical breakthroughs not yet made, the next layer is waiting. The next time gravity presses you into your chair, remember, you're not being pulled down. You're being held back. From the straightest possible path through a curved and beautiful cosmos that has been in motion for 13.8 billion years and has no intention of stopping. Thank you for spending this time looking at it with me. If this kind of deep, slow exploration of the universe is something you want more of, a like or a subscribe means the world and helps this channel keep going. I'll see you next time.